In this video, we are going to discuss the motion of a block. The problem is that a block of mass m is released from on a smooth incline from point A. After traveling through length of L, it strikes an ideal spring having force constant K. It compresses the spring and then gets pushed back. We have to calculate the time during which the block slides and then return back to its original position. So this motion can be divided into two parts. In the first part when it is sliding along the inclined plane, and in the second part when it is in contact with the spring. So during the contact with the spring, the motion will be simple harmonic motion, and when it is on the inclined plane, since it returns to its original position with the same velocity and acceleration, so that part is a periodic motion. So from A to B it is and back to A it is a periodic motion, and from B to maximum compression and then back to its original position, that is B, is a simple harmonic motion. So before discussing what the problem is all about, we'll discuss briefly about what is SHM. So in case of simple harmonic motion, we have acceleration, which is directly proportional to displacement from the mean position, and in the differential equation form we can write it as d2x by dt square plus kx equals to 0. So the solution will be either it is a sin omega t or a cos omega t. It depends on the initial condition, and if that is not known, we can write it in the form of a sin omega t plus phi, where phi is initial phase angle. This I'll discuss a little bit more in the next few slides. And as far as periodic motion is concerned, when the motion repeats, that is when the position or the velocity or the acceleration repeats itself after a certain interval of time, then that motion is periodic motion and the time is the time period. So before moving further, we'll discuss briefly about motion, simple harmonic motion under the influence of gravitational field. So let us consider a spring mass system of length L0 having mass m, and when this is released from rest, what we'll see is that if it is gently released, gently means there is no acceleration, the block moves without that means there is a kind of support always, so that it prevents any acceleration of the block. So in that case, the block will comes to its equilibrium position, where x naught is the distance traveled from the natural position or from unstretched length to equilibrium position, and I have taken downward direction as positive, and this downward direction is taken as positive, and origin is taken as the unstretched length. So this is our origin. So the block will move further to a distance x0 equals to mg by k. Now if we move this block further downward or displace it to a length a, then now this motion will be simple harmonic motion with an amplitude a. Notice again that this a can be greater than x0 or it is less than x0, so it hardly matters. So we can give the amplitude greater than x0 or less than x0. But in next case, let us consider a block of mass m. The natural length of spring is L0, and it is now in this case it is released from rest. Released from rest means there is no support, and this will instantaneously go in downward direction. So when we write the equation of motion, suppose this is our position A and this is our position, or we can write it as P so that we do not get confused with amplitude. This is our position P and this is our position Q. So when we write conservation of energy, because here both gravitational field and the spring force both are conservative in nature, so writing it, the total energy remains constant. So kinetic energy will be zero because it is released from rest. Potential energy of the spring is zero because there is no extension in the spring, and I have taken datum at P, so gravitational potential energy is also zero, and that equals to uh, kinetic energy at position Q, because the block will be momentarily at rest, so it will be zero. Potential energy will be half kx square, where x is the extension in the spring and mgx is the gravitational potential energy, since we have taken P as the datum. So when we solve this equation, half kx square minus mgx equals to 0, kx square minus 2mgx is 0. So after factor taking the factor x as outside, we get x equals to 0 and x equals to 2 mg by k. So these are the two solutions. So the particle will come momentarily to rest at two position. One is at x equals to 0 and another one is at x equals to 2 mg by k. So these will be the two extreme position and it will oscillate between these two. So first what we have to determine is the amplitude of motion. Now under equilibrium condition, when the net force is 0, we can equate that kx naught equals to mg or x naught equals to mg by k. So we can write x as mg by k plus minus mg by k. When we take the positive sign, the x coordinate will be mg by k plus mg by k, that is 2 mg by k, which is the one extreme position. And when we write x as mg by k minus mg by k, that is 0, which is the another extreme position. So we can write x equals to x naught plus minus x naught. So this is our first extreme position. We can say at one extreme, and this is our another extreme position. Now one thing that is to be noticed is that when the block, in this case when it is released from rest, it is not going to move any further from its natural length. It will remain there at its natural length. So it will not move any further upward when it is released from its natural position. It will first regain, it will obtain a equilibrium position, that is x naught. It will go further down x naught. This will be one extreme or the amplitude, and from here it will go again upward to x naught, but not above this position. This is the case when the block is released from rest, that is having initial velocity as 0. Now let us take the case when we are giving an impulse or a velocity to this system. So when we write again the conservation of energy between two position, so initial kinetic energy is half mv square and gravitational potential and spring potential energy is 0. In second case, the kinetic energy, that is momentarily at rest, so kinetic energy will be 0. Potential energy is half kx square and gravitational potential energy is minus mgx. Now so when we equate the equation and solve it, we get x equals to 2 mg plus minus root under 2 mg whole square minus 4k minus mv square divided by 2k, and after simplifying we get this equation. So it is mg by k plus minus mg by k, and within a square root it is 1 plus 4k mv square divided by 2 mg square. Now notice that mg by k is the equilibrium position. So mg by k will be x naught. So x is written as x naught plus minus x naught root under 1 plus 4 k mv square divided by 2 mg whole square. Now in this case, if we notice the second part of this equation, this value plus minus x naught is the amplitude, and the block will oscillate about this equilibrium position x naught, plus a as well as minus a. So we can say that this value is the amplitude a. So this is a here. This a is square root of 1 plus 4k mv square divided by 2 mg square, and this whole is multiplied by x naught. Similarly, and part of it is x naught and the other part is delta x. What I am trying to say is that this amplitude is greater than x naught because this value is greater than 1. So some delta x part is which is greater than x naught will be the part of the amplitude. Similarly, when the block moves upward from its equilibrium position, a is our amplitude, of which some part is x naught and other is delta x. What I'm trying to say here is that in this case, in the earlier previous case, the block was not moving from the upward from the position from where it was released, but in this case the block will move upward from the position from where it is released by an amount delta x. Now coming to the phase diagram, this is the second part which is required for our problem. So as far as phase diagram is concerned, suppose we start the motion at t equals to 0 when the block is at equilibrium position. I have taken origin at this location. This is our positive x, and in the negative direction it is negative x. So this is our positive x and this is our negative x. So when the motion starts and if it moves to a distance x, so the coordinate of the position is x. Here I have shown here, this is our x, and the block has, in this time interval t, the block has moved a distance x. So theta is omega into t, and we know that we can represent simple harmonic motion by uniform circular motion. So angle traversed during this interval is theta, that is omega into t. So we can write x as a cos pi by 2 minus theta because this angle will be pi by 2 minus theta. So this can be written as a sine theta. Similarly, velocity will be dx by dt, so it will be a omega cos theta, where theta is omega into t. Now, in this case, when the motion is starting from equilibrium position towards right, we see that in this circular part, which we have divided into 4 equal parts, so it is in first quadrant. Velocity and acceleration both are positive. In second case, when the block is at its extreme position and we are measuring time from this instant when it is starting motion from one of its extreme position, and this a is the amplitude to which this block has been stretched. In this case the amplitude is a. So if it moves a distance, some distance delta x in this time interval t, and x is the coordinate of the position of the particle from its mean position, so we can write x as theta, sorry, this is a, so we can write x as a cos theta, where theta is omega into t, and x is the instantaneous position and a minus x is the delta x which the particle has moved. Similarly, we can obtain the velocity v equals to dx by dt, and that is minus a omega sine theta, where theta is omega into t. Notice in this case the particle is in fourth quadrant. This is our fourth quadrant, where displacement is positive and velocity is negative. This we can verify from the simple harmonic motion. The particle at any instant during this time interval will be position will be positive and velocity is moving towards left, so it is negative. Similarly, in third case, when the particle is moving from its another extreme position, that is from negative a, sorry, this is should be a minus a and this should be minus x. So in this case x will be, and if the particle has moved a distance, suppose delta x, and that delta x will be a minus x, the magnitude of displacement will be a minus x. However, since it is in negative x direction, so it will be minus times delta x. So x will be minus a cos theta, where theta is omega into t, and we can write velocity as dx by dt, so it will be a omega sine omega theta. In this case, particle is in second quadrant, in this quadrant, in which position is instantaneous position is negative and velocity is positive. This can again be verified from the simple harmonic motion. So particle is towards left from its equilibrium position, so it is instantaneous position is always negative and velocity is positive. In the fourth case, when the particle is in equilibrium position and is moving towards left, so and if it moves a distance, suppose x, in time interval t, so theta will be omega into t and x will be a cos pi by 2 minus theta, and with a minus sign means its coordinate is negative. So x is minus a sine theta and v is dx by dt. So we can write v equals to minus a omega cos theta. Now in this case the particle is in third quadrant, both displacement as well as velocity both are negative, and this can again be verified from the simple harmonic motion, because in this case particle is moving from its equilibrium position towards left, so x will always be negative, and since it is moving towards left, so v is also negative. Now coming to our original problem, this block which was released from this position and it reaches just it touches the spring. Suppose this point is P and this is Q. So during PQ the motion is not simple harmonic because it will just slide, and when we apply conservation of energy between point P and Q, since there are no frictional force present here, so we can write half mv square equals to mgl sine beta, where L sine beta is the height through which this block has fallen. Similarly, when we write the when we draw its free body diagram, the forces acting on this block will be mgl sine beta, mg sine beta, and there are no other force, so acceleration is constant. So we can use the equation s equals to ut plus half at square, and when we are using this equation, we can write this equation as half gt square equals to Ly sine beta. So this is our equation. So we can calculate the time taken to move from P to Q. Now after from P to Q the motion after Q the motion will be simple harmonic. It will come to an equilibrium position x naught. In this equilibrium position x naught, that is kx naught, will be equal to the net force, that is mg into sine beta, and this angle is beta. After this equilibrium position, this block will move further so that it comes momentarily to rest. Once it comes to rest, um, it will move towards right. Again it will reach to its equilibrium position. Then it, because of here this net force will be zero, but because of velocity it will move further, and when it reaches its natural length L0, there will be no contact in between spring and this block. So from again here to this Q, motion repeats itself, so motion will be in fact periodic motions. So we can say that total time taken will be part of time that is required to move from position Q to P and then back to P to Q, and part from P to its maximum compression and then back to its position P. So if we write the equation as uh, if we take the conservation of energy equation, and suppose this is our position P and this is our position R, and if we write conservation of total or mechanical energy, because there are no non-conservative force present here, so we can write it as half mv square plus 0. Half mv square is our kinetic energy potential, and this 0 is our we have taken datum at this location. We have taken datum at P, so this value gravitational potential energy will be 0, and energy stored in spring will also be 0. And when we equate it to position R, where the kinetic energy is 0 and energy stored in spring is half kx square, and gravitational potential energy is minus mg sine beta into x, because I have taken this direction as x, so drop in height will be x sine beta. This height will be, if this angle is beta, then drop in height will be x sine beta. This is so when we equate this equation, that is mgl sine beta equals to half kx square plus 0 minus mg sine beta into x. This is a quadratic equation. It will have two solutions, and when we solve it, we get finally this final expression, that is x equals to mg sine beta by k plus minus mg sine beta by k into this value. So now this mg sine beta by k is x naught, because at equilibrium position the net force, that is the gravitational force, that is mg sine beta, and this should be balanced by k into x naught, so x naught will be mg sine beta by k. So finally we obtain x equals to x naught plus minus x naught root under 1 plus 2k by l 2kl upon mg sine beta. And notice that this value, because this block will oscillate about its equilibrium position x naught, so this value is our amplitude A. Now when we use the phase diagram concept here, what we will observe, that during the motion, that is from the natural length L0 to x naught, the block has to move a distance x naught, then it will compress the spring to its extreme position, then further it will return back to its equilibrium position. This is our equilibrium position, and after that it will move further to a distance x naught, and then it will leave the block. So what I am saying here is that when this block starts from here, it will move a distance x naught, then it will move to its extreme position, that is A. Here it will come momentarily to rest, then it will move back again a distance A. After that it will move to its natural length L, and during this interval it will travel a distance x naught, and from here it will leave the contact, and then there will be no contact with the spring. So total time taken will be the time taken to move this distance, that is pi by 2 minus alpha, plus time taken for this extreme position, that is 1/4 of time period, then again moving from its extreme position to equilibrium position, this is again 1/4 of time period, and then again to move a distance x naught, that will be the angle that it has to travel is pi by 2 minus alpha. So this time will be, because we know that omega into t is theta, and here theta will be pi by 2 minus alpha. This equals to pi by 2 minus alpha. So we can say that the total time taken is twice of pi by 2 minus alpha divided by omega plus t by 4 plus t by 4 plus time to slip from this position to the contact with the spring and then return back to the spring. So from here it will move here, this is the natural position, and here it will move, then it will move x naught, then further a, then it will return a, then again x naught, and from here it will return back. So total time will be t by 4 plus t by 4 plus 2 times pi by 2 minus alpha divided by omega plus 2t. This 2t, small t, is time to return to its original position where there is no contact with the spring. And this cos alpha, from this diagram we can see that cos alpha is x naught by a. So after rearranging this value and substituting omega equals to 2 pi by t, the total time is t by 2 plus 2t upon 2 by omega multiplied by pi by 2 minus alpha plus 2, and this value is L by sine beta. Sorry, this is a mistake. L by sine beta. Sorry, it's okay, it's okay. Sorry for the it's okay. So these are correct. So total time taken will be finally, it will be t minus t into alpha upon pi plus 2 into square root of 2L sine beta by g. So this part is our time for this simple harmonic motion, and this is the time for ascending and descending along the inclined plane. So this value is our total time taken, which partly contributed by the simple harmonic motion and partly by this periodic motion. Thank you.